Alrighty, so 1.4, composition of mixtures. I also included types of reactions in this section because I wasn't quite sure what section to put that in, but it does fall under Unit 1, so I put that right after talking about compositions of mixtures. So one thing to know is the charts on the printouts I gave you. So one of the charts is this flow chart here, and then the other chart as well. Knowing the definitions of all these things is important. You did read about them in the summer homework, but if you still want more clarifications on those definitions, then you'll want to check under the references under Unit 1. There is a reading link, and it talks about these particular terms in case you are confused. Also know relative proportions versus not. So like what does happen in proportionality, like if things come in one thing or two things, or if it comes in multiple things, like how does that work? And that goes alongside with this clarification on compounds. So molecules are used for covalent compounds, and atoms and ions are used for ionic compounds. And they're in fixed formula units that are proportional. So, for example, if I look at sodium chloride, that's going to be Na and Cl. Na is going to be +1, Cl is going to be -1, and so they exist as one sodium and one chloride ion combined. And so that's the relative proportion of those ions in the NaCl compound. They will always exist as one sodium for every one chloride. For any other ionic compound, it would exist based off whatever the charges are. So those are like relative proportions. Versus molecules, molecules exist as they are. So if I have CO2, it will always be CO2. Like if I'm talking purely about carbon dioxide, it will never be C2O4, even though proportionally that's the same thing if I reduce it down. Molecules only exist as whatever compound it exists as. CO2 is different from C2O4, so just knowing that. And so here's the other chart that I was talking about. There is some definitions under these charts, and you can see where it goes through and some examples of that and all that stuff. Okay, so for this your turn, you have it printed on your paper. You're going to talk about pure substances or mixtures here, and then if it's a pure substance, is it an element or a compound? If it's a mixture, is it homogeneous or heterogeneous? For the picture versions, you want to do the most specific label as possible. So for example, is it an element or is it a compound? If it is a mixture of them, then what is in that mixture? Is it a mixture of elements, or is it a mixture of compounds, or is it a mixture of both? So pause this video, do this yourself, and then I'll show the answers in a few moments. Alrighty, so let's go ahead and put the answers up. So here we go, bam. Ta-da! If you have questions on these, just let me know. One thing that I did not do is I named these compounds, right? So I didn't say that they were molecules versus ionic compounds because it's hard to tell. It is easier to tell when you have a bigger model of how they look like. And ionic tends to be something like this, where they're kind of all together if they are different atoms of different elements. So just be very careful about stuff like that. In general, all these compounds are probably going to be covalent compounds just from the nature of them being separated and not together, but, you know, it could not be too. Okay. So, mixtures. We can separate mixtures by 4 different ways. You do need to know all 4 different ways and how they work. Some of these we'll do as labs. Some of them I don't have the equipment because it's gosh darn expensive. So we'll be doing a future mini lab. It's a very small, quick lab of stuff like this. So let's go through each of them. But before we do actually, though, there is this FRQ. It is only part A of the FRQ, and so try to do this yourself. It's based off intuition, I would say. So, you have your equation up here, and then you have your investigation, and then you have some information about the problem. You have some stuff, and you're doing some stuff. I have some helpful hints on the side, so go ahead and try this out, and then I'm actually going to walk through it because I decided not to make this on the slides. Okay, so you want to, read the thing. And like I said here, on the test, honestly, cross stuff out that doesn't matter. And I'm actually going to go ahead and do that. So, to show why things are the way they are. So, we're investigating a reaction of nitrogen oxides. Great. One of the reactions requires an equimolar mixture of NO and NO2. Equimolar. So even if you don't know what that term is, break it apart, right? Like equal, and molar, like moles. So we have an equal amount of moles of NO and NO2. So we have an equal amount of this guy and this guy. And if I look at this picture, whoops, I can notice that I have 1, 2, 3, 4 of the, let's see, what is this? NO2, and then 1, 2, 3, 4 of the NO. So that is indeed true, just based off that. And then it produces by using the reaction above. So we're looking at that reaction. So do I need any information on here? I guess the equimolar part, but I could have easily counted that out. So like I'm literally just going to cross this out. In the off chance I need to review this problem after doing hella different parts, because again, this is part A. So if I did like part B, part C, part D, and I want to go back to A, I don't need to read those parts again because I crossed it out, because who cares? I already know the information I needed. I can also potentially cross this sentence off, but again, it just depends on like what the other parts are. So we have a particle representation, great. We have the equimolar mixture, cool. It's in a flask at the completion of the reaction between, completion of the reaction with NO and O2. So we have used some of this, both of these things, in order to make the NO2s that exist here. In the box below on the left, so we're here, we're going to draw particle representation of the reactant mixture that would yield this. All right, and so we have this key here. So we're drawing the particle level, and then we're doing the reaction or reactant mixture that would yield the product. And then we have that. Okay, great. I'm literally just going to cross out everything that I already understand just from like seeing a key and stuff. And so, that's one strategy of doing these problems. If you have a bunch of text, just cross out stuff you don't need. And so I like to mark stuff as I need. Okay, anyway. We're going to see our products. I'm going to go ahead and circle the products just to like emphasize them here. So I have one here, I have one here, I have one here, and then I have one here. So those products need to be back to the reactants because that's what reacted, right? And we have extra NOs just chilling. So I should have these extra NOs in this diagram already. So I'm going to actually go ahead and draw those. And the reason behind that is because these guys weren't used in order to make these NO2s. They were just chilling in the original mixture, and so they don't actually end up mixing with the O2s that were originally there. So that's why I am drawing it from here to here, just because I know that those ones didn't react. So now I'm going to look at these four. And so there's multiple ways of doing it. I'm going to do it like in my version in my head, the intuitive way, which is just going backwards. So if I just like cross out particles and then draw them here and then just keep crossing them out as I'm trying to make these reactants, that's how it works in my head anyway. And so I'm going to see for one product, I can cross out these two oxygens to make an O2 because that's an O2 here. And then I'll do an NO right here, an N and an O. So I just crossed out from two different ones. And so those will be like that. And then I could do another NO over here. And so I'll do that. And then I could do an oxygen O2 from here and here. And then I can do an NO from this nitrogen and this oxygen. And then I can have an NO from here and here. Is that the best drawing? No. But it works. It works. It works. And so what you know, when you're doing these problems, try to think of intuitive ways of doing it. For example, me crossing stuff out. You could have easily done this based off looking at the coefficients on the reaction here. So since I made 4 of these, I should have 4 NOs and 2 O2s because this is just based off the ratio here. If I only had 2 NO2s, I would have 1 O2 and 2 NOs that were from the products being formed. So that's another way of doing it. I just like the crossing out way. This FRQ would be 2 points. 1 point would be earned from just drawing the correct molecules representing NO and O2. And then 1 point is if you did atom conservation. So notice that the number of N's and the number of O's are the same on both sides. If I counted all how many N's there were and how many O's there were, they're the same amount. And so that would be the other point. And so FRQs can sometimes be graded like that. It really depends on the FRQ. Cool. Okay, so, oh, that's an old thing, sorry. That'll be for section 1.3, I believe. Well, anyway, so we need to know the 4 different ways of separating, like I said earlier. So you need to know these and how they work. And so let's talk about each of these. So we have separating liquids based off different boiling points. I use BP for boiling points. Usually you're separating the smaller BP. And so you have to know how the system works. This is one of those expensive things that I don't have, which I hope to get someday. But it's a very common lab you do in college, usually in OChem, I think. Well, anyway, so what happens is you'll have something heating, so either here or here, however you want to heat it. And then it's in some kind of flask or whatever, and you have a mixture of 2 liquids. And so this mixture of 2 liquids, again, it's heating up. So whichever is the lower boiling point is going to heat up first. So for example, if I had 2 things in it that was 50 degrees Celsius at boiling point and 75 degrees Celsius boiling point, the 50 would, evaporate first because you reach that point of temperature first. And so that 50 degree boiling point liquid is going to travel up. And the thermometer is helping you, regulate the heat that you need to do. Because again, if you know the boiling points of the 2 different things, you can control how much heat you're using in order to evaporate whatever you're trying to evaporate. And so that 50 degree boiling point liquid is now a gas, right? Because it has evaporated. And so it's going to travel through this one tube here called the condenser. And so what happens with the condenser is actually surrounded by another tubing. So there's the inside tubing where the gas is going to be, and there's this outside tubing with these 2 little spick thingies. And so you have cold water going in. And so cold water is going in, it's surrounding that tube of gas, and then cold water is going to come out because you just want to continually keep that water cold. And so by doing so, any gas that was in here of that 50 degree boiling point liquid is going to become liquid now because it was a gas, it's getting cool. When you get colder, you'll change states of matter. So it's going to get cooler, and then it slowly drops off into over here. So this is called the distillate, and you're going to collect that lower boiling point. And so eventually, if this was, let's say, 2 different liquid mixtures with 2 different boiling points, the higher boiling point would be left behind, and the lower boiling point would be here. If it was multiple liquids, then you can collect whatever up to the first boiling point and maybe a little over. Then once you think you've collected everything, then you can take that out, put a new distillate chamber, whatever container you want to put in, and then you'll go to the next boiling point, try to get all that liquid out, and then eventually until you get whatever liquid is left behind. And that is why it's called fractional distillation, because you're separating them into different fractions of materials. Okay, so here's a quick example question. So read this to yourself and then try to answer it. It's similar to some MCQs I've seen before. I'll go ahead and pause for a little bit before talking about it. Okay, so if I'm heating up the liquid, it's a mixture of ethanol and water. Since ethanol has a lower boiling point, that's going to boil out first, and so you're going to boil it at around 78, 79, 80 degrees. All of the ethanol will become gas, then it'll travel here in the condenser, it'll get cool and become a liquid, and then you'll collect that ethanol over here. Coolio. All right, next thing is filtration. So filtration's pretty easy. You have like a funnel, and then you got filter paper, and you have a mixture of like solids and liquids. And so if I have a mixture of solids and liquids, I want to separate that liquid from that solid. And so if this was the mixture here that had the liquid and the solid would get caught in the filter paper, and then the liquid would go through the filter paper into the funnel into the flask. This only works for heterogeneous stuff. If that liquid was multiple things, you can't separate it, using this method. So, to go back to this previous example here, if I had a mixture of ethanol, water, and sand, for example, in this case, I would only be separating the sand, but the liquid would still be ethanol and water. So that's pretty much how you would separate stuff. So it only works for heterogeneous mixtures separation. You also cannot do solutions. So as a reminder, a solution is a ionic compound where the ions are in the water and it's aqueous, usually, not always, but usually. And so you can't separate salt from a solution because the ions are dissolved in it. It doesn't work for this. There's another way to separate them, which we'll talk about later. So NaCl is salt, and so salt in water, when it's dissolved, you cannot separate like this because the salt is literally dissolved. It is not a solid, so therefore you're not going to be able to collect that solid there. Here's a quick little example. So try this example question, or two rather, and it tells you the scenario here. And then I'll show the answers in a few moments. All right. So, answer. Bam. The salt water is going to go through, and then what's left behind in the funnel is the sand. So remember, salt water is dissolved salt in the water, so it'll collect down there. And so it's not pure because it's still salt water, unless I wanted to just have salt water. But if I wanted to take out the salt from the water, that would be a separate thing, not through filtration. Cool. All right, chromatography. So chromatography is something that we will explore more in a future unit. I'm just going to introduce it now and vaguely talk about it. But essentially you're trying to separate solids or liquids based off polarity. And so for now, I'm just going to say polar stuff dissolves in polar stuff and non-polar stuff dissolves in non-polar stuff. That idea isn't a good explanation for the AP test, but it's something to just vaguely remember. Again, we'll talk about chromatography in more detail once we talk about polarity later. For now, again, it's just this. And there are two versions you have to know. You need to know TLC, which is thin layer chromatography, and then column chromatography. And so, again, I'm not going to hardcore talk about this, but essentially we have, for TLC, You got a solvent, you have a sample on this plate. It could be paper, it could be something else. That sample is going to separate as that solvent travels up, and so you can see the two separations here. And it is again based off polarity, which we will talk about in a future unit, because I see no example question about this. So this is it for now. So cool. And then column chromatography, similarly, we are doing it in a column, as the name implies. You have a sample and then something called a stationary phase, which I'll talk about more in a future unit. And so again, it's similar to paper chromatography, which was TLC. TLC could also not be paper, but typically it's paper. And we'll do a lab on this too, but we'll do that when we are in the other unit because we need more information. So the stationary phase for this is going to be some kind of silica gel or an absorbent. It really depends on the thing. You're trying to separate based off shape or size of the particles, again based off polarity, which we'll talk about later. And so the mobile phase will go through that. If you're like, what is mobile phase? Again, it's okay. we'll focus this more in a future unit. And then you're interacting with IMFs, which is what we'll talk about in unit 3, I think. So, yeah. Mobile phase is the solvent that you're going to put through it. It's with the sample that you're trying to separate. And then you're going to collect fractions. So again, if you're like, whoa, she's throwing so much vocab, I wouldn't worry too much about this other than there's 2 chromatographies. They separate by polarity, and we'll talk about it more later. You can see this diagram. Just know like vaguely how the diagram is, kind of, and then we'll talk about it more in the future. Cool. There are many uses for this. I might as well just talk about the uses now in case you are curious. In drugs, if you're trying to isolate active ingredients in drugs, you can use column chromatography to get the pure substance of whatever drug you're trying to make. I'm talking about prescription drugs. Could it be for something else? Whatever. Removing impurities. So if I'm trying to remove certain things from the mixture, it is good for removing impurities that I don't need in whatever mixture I have. Usually the stationary phase is polar, which again we'll talk about in a future unit, and the mobile phase is nonpolar or as close to nonpolar as possible. Collecting the blue sample, if it's very slow compared to the yellow, we need to change the solvent. So like I can collect this yellow sample, right? But look how slow this blue one is. So I would change whatever thing I'm putting into the top. And then we can, get it faster. If everything is colorless, there's no easy way to do this. You would just need to make hella tiny samples and then test them out using other lab techniques. But if they were colored, like here, then it's a lot easier. It's like, look, yellow, easy, and then blue, cool. Cool. Okay, the other way of separating mixtures is crystallization or hydration, depending on which way we're going. And so crystallization, we're making a solid from a liquid, and we're precipitating it out. One or the other, right? It's a physical change if I'm changing it based off temperature, because if I literally am just making it hotter or colder in order to get what I'm trying to get, cool. It's a chemical change if I use something else, like acid. If I use acid, I'm going to change the chemical breakdown of that thing, and then bada bing, bada boom. Crystals can be formed in different ways. So we have single species of atoms, meaning I only have one type of atom in it, or molecule, I guess. It really depends on what I'm talking about. So for example, if I'm trying to get just sodium, I can do that by forming crystals and making just sodium. Well, maybe not sodium as a good example, but in general. And then I could do different species of ions. So if I wanted fluoride ions, then I could separate those. I could do larger molecules, so if I want a whole bunch of proteins for some reason, from like cells or whatever, I can get those clumps of proteins by making crystals. And for large molecules, I'm talking like really, really big, like C20H50 or something. That's harder to crystallize, but, whatever. Crystallization, as I said here, is the simplest way of purifying because most of the time you're just changing the temperature. I'm trying to make it colder in order to make a solid, for example, or if it's a gas, then I'm going to make it colder to get liquid. Hydration is the opposite thing, kind of, where if I have some crystals, I want to dissolve it in water. Okay, so here's a quick your turn. Go ahead and read it. Try it out. I'll talk about it in like a few moments. Okay, so we have seawater, and then it's in a container, it's in the sun, it evaporates the water. The crystals would be whatever salt and solids are in seawater. So obviously we have like the salt that we think about. There could be other kinds of salt in there. A salt is just an ionic compound. They're all salts, even though we think of salt as like table salt, the stuff you use in cooking. That's NaCl usually. But anything else that's solid ionic, usually we consider a salt. Cool. Okay, reaction types. Should I make this a different video? Maybe I'll put 2 videos. Okay, I'm going to stop this recording.